So, to not further cut into your presentation time, please welcome with a very warm round of applause Dan and Laura and Car Hacking Back to the Future 1970s Style Part 2.
So is this on now?
It is.
Hello? Cool. Move the way. Is this one off? Hello? Hi everyone, welcome to Car Hacking Back to the Future 1970 Style Part 2. I'm Dan Smith and this is Laura Hyatt. Today I'm going to be talking about my continued journey on what I've been doing for the last couple of years. Since I was here 2 years ago, last EMF. So a little bit about me. I first attended EMF in 2014. I spoke at last EMF, which was the previous talk to this one. I'm an engineer working in automotive security, and you know, I have a bit of a mixed background. It wasn't until quite recently that I actually discovered that I am an engineer now at heart. And you know, I have a background in computer science and also cars and a few other things. Yeah. So for those of you that didn't attend the previous talk, I'll just quickly go over, give you some context of what I've actually been working on, because otherwise it's not really going to make much sense. So this is the car that I pretty much have worked on the last 4 years, like solidly. It's a 1974 Ford Escort Mark I. It's my first car. I've owned it for over 10 years now. It's still rocking the original 1.3 Ford Kent Crossflow engine. You know, some of the things I've done to it over the years, it started off with a 3-speed automatic gearbox, and then it was converted to a 4-speed manual. And to make it a bit more fuel friendly, it's now got a 5-speed manual in it. And it's mostly still looks pretty stock, and it's got like a stock interior. It's just, you know, just an old car really. And slowly over the years, I've added things to it. You know, the first thing that I did really was convert it over to fuel injection. So this is my original setup that I made a few years ago, 4 or 5 years ago. It was a single point injection, so there's one injector that serves all 4 cylinders, and I added a turbo to it. It's running 7 psi boost. It's running a Mega Squirt 3 ECU, and it made about 120 horsepower with about 130 pound of torque. And yeah, you know, it's a fairly nippy car for that amount of power in a car that small and doesn't weigh much. And it was nippy up until the point where it effectively melted a little bit, a couple of the pistons. So yeah, it's been off the road a few years now. This is the Mega Squirt ECU. It's the main computer responsible for controlling the engine, controls all of the fuel, does all the calculations for the air, and it controls the ignition coils. You can buy it pre-assembled or as a kit. I bought it as a kit, came from the US, soldered it together, did a lot of bench testing, got it working, got it in the car, started the car, pretty good. It's a fairly steepish learning curve to kind of get your head around it, but once you know a little bit about cars and a little bit about embedded electronics, it's not too bad, and it's a very capable ECU if you're willing to put the time in to learn it, and it's quite cheap as well for what it is. So kind of that summarizes the previous talk, like all the things I did previously, and then in the last couple of years, this is kind of what I've done on the engine side. So I've gone from the single point injection over to multi-point, which has been an interesting journey. So now there's 4 injectors for each of the cylinders, like you would find on a modern car. It's also got an electric radiator fan. So the fan can be turned on at will by any time by the ECU when it needs it. So that's quite handy on a cold day during the winter when, previously you start the car and the fan immediately would come on and start cooling the engine because it's directly belt driven. Well, now it doesn't come on until it needs. Saves a bit of power, engine warms up faster, all's good. It's also got like electric water pump, which again is PWM controlled by the ECU directly, so the ECU can make the decisions if it wants to speed or slow down the water pump. It's got boost controller, so it can dynamically change the power, the turbo's output in when you're driving, which is good because you can dial the power down when it's in the wet, when you're on the motorway, when you're overtaken, because you get wheel spin quite easily, and there's no, traction or anything. It's also just got like an extra few sensors just to make the drivability a bit better. It's got a math sensor, which is similar to what you find on the modern engine today. It's got an IAC control valve, which again just makes it a bit easier starting on a cold day. I'm currently working on putting the clutch switch in it so you can have launch control, like, Ferraris and stuff. And it's got lots of extra sensors dotted around the engine bay because last time when the engine kind of went kaput, I didn't have enough data. I didn't have enough sensors which kind of indicated where the problem was coming from. So I've added them in this time and they're all there, and all that information is over CAN, so you can do a lot with it. But the other things that I've been working on, I've mainly been fabricating parts a lot for the last couple of years, and the big game changer for me, I'm on the right slide. Yeah, the big game changer for me was I've been using 3D printers for a while, but it wasn't, until about 18 months ago or so that I actually got one at home. And as soon as I got one, it just changed how I worked altogether. I was no longer having to spend so much time fabricating parts, out of aluminium and steel. It was more time was focused on actually designing the parts and perfecting that design, and then once it was right, it was just clicking the button, print, and off you go. So I've been using that for lots of different things in the car, which we'll cover now. So originally I just started using it to prototype parts that go in the engine bay, like brackets and holders and clips and things like that. Nothing that, I might use it, I might not use it. If it breaks, it doesn't matter. And I quickly moved on to doing larger parts. So in the photos there, everything that you can see in red has been 3D printed. And the main part that you can see is the intake manifold and part of the turbo plenum. And that's all been designed using Fusion 360. The reason why I designed it was because those parts that I need are not available off the shelf for that engine, so I'd have to make it myself. If I pay someone else to design it and make it, that costs a lot of money. So I designed it myself using Fusion 360. The measurements were taken using measurements from some of the original Ford manifolds and then adapted to suit my design. So it's mated to a Cosworth YB turbo plenum. And yeah, the ability using the 3D printer to iterate through the design very quickly and test out new ideas was greatly beneficial. And ultimately, the model that I designed, that I put so many hours in, I was actually able to send over to a fabricator, and they were able to use the same model to make what I designed out of aluminium. So the bits that were red in the previous slide, they're there now, but they're made out of metal, aluminium, and the design is literally exactly the same as the 3D printed model that I made. The reason why I didn't use the 3D printed model is because it might work for 2 minutes, but plastic bolted directly to a hot engine with pressurized air going through it probably isn't a good thing to do. Yeah, so ignore the engine in that photo. That's just a scrap engine. I just put that in there just because the engine that I blew up, I took out. I put that one in just so I can, just so I had something for reference points because I've got to make a new wiring harness. So I just put it in just so I could get all the wires perfectly to length. I kind of then moved on to actually trying to use the 3D printer to make a functional part that would actually be used in the engine when the car's running. So the part that I made there is an adapter that goes in between the Gen V throttle body, which is 48 mil diameter bore, to a Cosworth YB throttle body, which is 55 mil. This part will be under pressure. It won't have any fuel or anything near it, but it will be under pressure. It'll be very close proximity to the engine, lots of heat, lots of vibration, external weather, all sorts of nasty things. It's also got to be sealed on both sides, so it's got to be ideally perfectly flat, with like an O-ring on the one side to stop any boost leaks. Otherwise, you're just throwing power away. It's also got to have some bolts threaded into it because the actual Gen V throttle body's got to mount to it, and it's got to be held. And I haven't done the final version yet, but the final version will be printed using Carbon X filament, which I think is from the States, and that's carbon fiber reinforced nylon that supposedly passes the PA 66 spec, which is commonly used for plastics in the engine bay. So I don't know, it might last. It's a simple enough part. I can always carry one in the engine, in the car with me if it ever went, and I can change it on the side of the road, or I could just get it machined out of aluminium. But, I kind of want to try doing a functional part, and 3D printing a plenum or an intake that's just too risky. But this part's simple enough that, I might as well try and see what happens. And I know people have done 3D printed parts with naturally aspirated engines, but I've not really seen anyone do anything on a turbo, so I thought, why not? I might as well try. And the part there, so that's the design on the left, just for reference. And then on the photo on the right, it's just behind the throttle body. It's the slightly dark gray. You can kind of see it. So yeah, but that's got to be, that's in PLA at the moment, just for prototyping, just because it's cheap. But that's going to be in carbon fiber. So I don't know, see how that goes. Other things I've worked on 3D printing. This has actually been quite useful. I've actually used it to reproduce proprietary Ford connectors that were manufactured a long time ago in the 70s, that you just can't get anymore. The main connector, the most interesting one, is the main engine firewall connector, which is a sealed unit. It's made out of some kind of rubber when Ford made it. When it came from the factory, when they stamped it together, it fused, you can't get it apart. It looks fairly watertight. So if you kind of go in there and start cutting it up, you're probably going to reduce the reliability of that section of the harness, and considering it's the main one, is probably not a good thing to do. So I got my calipers out, measured it all over, and started putting together a design of my own, and it actually worked out pretty well. It's printed using a partially flexible filament, again from the States, by a company called Ninja Tech, using the cheetah filament. It's very, very strong, even though it's flexible. It's resistant, supposedly, to oil and fuel, and it's got a fairly high strength rating. And yeah, I'm actually able to reproduce some of these connectors that you just can't get anymore, and that's very, very handy. And I've actually sold a few of those because there are people that are interested and you can't get them. So the other thing that I have been working on as well, which I previously talked about in my previous talk, is the digital cluster that I built. So this is how it looks today. Literally, I took that photo today. I brought it here with me. It's still very much a prototype, but I have sunk a lot of hours into it. And it's definitely been an interesting project to learn and work on. Both hardware, prototyping, designing, fabricating, and a lot of software as well. So it's running a Raspberry Pi 3. Every time they release a new version, I just take the old one out, put the new one in, and you get a little bit faster performance. It's got a couple stacked Raspberry Pi shields on it. The first one is, again, off-the-shelf product, Sleepy Pi 2. That's the power management board, effectively. It maintains a state machine. the current state of the vehicle ignition, so it knows when the ignition's turned on or off. When it's on, it effectively turns the Raspberry Pi on, starts booting it up. And again, when the ignition state has been lost, after 10 seconds, it starts a clean shutdown. And that can be turned on independently. If the power management decides it wants to turn on, it can turn it on. The rest of the car can be turned off. So if you wanted to remote into the car and start it up or something like that makes that possible. And the other shield is the PiCan 2, and that enables the Raspberry Pi to communicate with the Megasquirt ECU via CAN bus. And so you can display whatever you want from the Megasquirt up on the screen, RPM, speed, all the sensors, And the other bit that I've also added, I've just bodged in some perf board, and that allows me to accept some of the more analog vehicle signals and inputs. So from the indicators and the alternator and the main beam, and that allows me to show the graphic up on the screen as with the original cluster. And the software, it's pretty custom, but again, it's kind of simple once you got your head around it. I'm using a toolchain called BuildRoot to build a customized image of Linux. It's running a fairly recent kernel. They release updates about every quarter, so every quarter you get a slightly newer kernel, a bit newer firmware for the Raspberry Pi, which is cool. They also do an LTS release, which I'm currently using. The GUI components for the cluster, what you see is made up of Qt5, Qt, and PyQt. I use PyQt just for prototyping. The boot time at the moment from totally off to totally on working is about 5 seconds. I haven't spent much time trying to optimize it, so I'm sure you could get that down if you really wanted to. Getting rid of PyQt and going over straight to native C++ would definitely help that. And the power management, state machine, all that's wrote in C++. And it's kind of cool. It's all linked into GitLab. I have runners at home, so anytime I make a change, it automatically kicks off a build, and an hour later, I have a finished image that I just flash straight onto the Pi. It's really cool. BuildRoot is awesome. I really like it. For those that haven't used it and have Raspberry Pi and don't want to use Raspbian, or they want to try something their own and get their hands in a bit more, they want to get a bit more dirty, but without kind of going full on, Linux from scratch, Raspberry Pi edition. Those are the commands that you need literally to get a custom Linux running, built using BuildRoot. It's very, very simple. Once those commands have ran, after an hour, just flash it using something like Etcher. And the documentation that they have is very, very good. It's pretty easy to understand once you've started tinkering around with it a little bit. So I built the stash. It functions fine as a prototype. I kind of wanted to test it more than just on the bench. On the bench, everything worked fine. But in the real world, I know obviously there's unexpected problems that you run into. But the car that it was built for didn't have an engine that ran, so I needed something to do. So I just took my daily driver, which is a Mondeo, and I took a couple of tools that I had, a Contact and a Panda, and I just reverse engineered the CAN signals for the RPM and the speed. And I then just went into my cluster code and just altered those couple IDs, flashed it, and bodged together a very crude model, printed it, and combined it with some hot glue, and just shoved the dash in there. And just bodged together like an OBD little connector that just plugs into the OBD port. And I ran that for like 2 months, daily. My primary concern was at night it would be too bright, and you wouldn't be able to have much visibility, but everything worked out fine. So when the engine eventually drops back into the car, that'll be going in. And there is actually audio, but it's playing from here. But yeah, you can see it. You can see it revving. It's got no lag whatsoever. It's really responsive, and that's just the OBD down there. I think that's me done. So that's kind of more the hands-on side, the fabricating, the engine and the car and the electronics and the wiring. But another bit that I wanted to do was actually start connecting the car online. And that's where Laura comes in to talk about some basic telematics to remotely monitor and control the car.
So yeah, that's me. So yeah, I'm going to be talking briefly about AWS Greengrass and how I incorporated it into the car. So to kind of give you a bit of context about basically why I'm here. So I've kind of been on an AWS journey, I guess, this year. So in January, I got my cloud practitioner certification. In May, I did my solutions architect associate, and then about 3 or 4 weeks ago, I got the developer associate. So really for the last year, because obviously I've been studying beforehand, I've been learning about AWS, and Dan wanted to basically connect the car online. And so he was like, why don't you get involved with it then and use the skills that you've been learning in AWS to help me out? So this is why I'm here. So I'm going to briefly talk about Greengrass. Now, I'm sure many of you have used AWS, but has anyone used AWS Greengrass before? Okay, that's good. One person. That's good, because I was worried that I was going to be preaching to the choir here. But essentially, Greengrass is a service that allows you to run AWS compute functionality locally on connected devices. So essentially, you could run a Lambda function, in Python, Node.js, whatever, and run it locally on your Raspberry Pi. Now, the reason why this is obviously good is that it means you can connect to physical hardware. So you can use your Lambda function to trigger GPI opens. And so you can kind of see why this could be useful in a car, for example. So we obviously have used a Raspberry Pi to power functionality in the car. So the AWS projects that we did. So there were 3 that we wanted to do before this talk. Obviously, we're going to do some more following it, but there was a limited amount of time. Now, I just want to point out that 2 of them use Greengrass, and 1 of them doesn't. It works, and it's absolutely fine. It's just that it runs locally on a Pi because essentially Greengrass runs in a sandbox, and there are some limitations with that. I'm obviously going to explain these in more details in a minute, but just to give you a brief overview, the remote engine start. So this is my favorite. It's the first one I did. And essentially, you can remotely start the car engine from anywhere in the world is basically how it works. The GPS tracker was the next one that we did, because obviously it's a classic car. Dan has spent so long working on this. Imagine if it was stolen, it'd be devastated. So we wanted a way to be able to track the car in real time in case it was stolen. And then the final one was the car telematics using CAN. I know Dan briefly mentioned CAN. This is the one that we didn't get working in Greengrass. For some reason, and obviously we're going to continue working on it, we couldn't get the CAN Python module to work with Greengrass, but we do have it working just locally in a normal Python script on the Pi. So, okay, let me explain the remote engine start. So I'm going to show you basically a brief video, because obviously I don't have a car here to give a demonstration. So this is a little video that I just filmed a couple of weeks ago. Sorry, the audio is not great.
And I've got a AWS IoT button, which when you press the button, it connects to AWS, which then connects to AWS Greengrass locally on the Pi. Now this triggers a Lambda function locally on the Pi, and I wrote that in Python, and that turns on the relay board, which is connected to the starter motor, which then starts the car. So let's have a go.
Thanks. So yeah, that was actually my first thing that I did. So obviously it's like my baby, and I'm really, really proud of it, because like I said, it's kind of, I'm on this AWS journey at the moment. So essentially, like I kind of explained, Greengrass is installed locally on the Pi, and then that obviously connected the GPIO pins to the relay board, which is then connected to the starter motor. And then basically I wrote just a really simple Python script on Lambda. Essentially all it is like an on-off script. It's about this big, the lines of code. And when it runs, the Lambda function is executed locally on the Pi, and that basically turns on the relay board, which then starts the engine motor. So it's actually a pretty simple concept, but obviously it's quite a cool idea. But then essentially to make it truly remote, I could basically configure an IoT button. So I don't know if you, obviously there's a little picture there. I don't know if you've used one of these before. It's essentially like the dash, but effectively I configured that so when the button was pressed, it would execute the Lambda function. And what this kind of means is that I could have the button with me, say, in Australia. And as long as I'm connected to the Wi-Fi or 4G, and obviously the Pi is turned on, I could press that and the car could be in England and it would remotely start. So it's kind of a cool thing. So that's what we did first. Now, with this, once this was successful, we moved on to a GPS tracker. Now, we've got a GPS receiver, which is connected to the Raspberry Pi. And basically, again, Greengrass is installed on the Pi using a GPS Python module, wrote a small bit of code that eventually outputs longitude and latitude coordinates of the car in, I say real time. Wrote it that it does it every 5 seconds because every second it kind of gets a bit crazy and you can't really read anything. So that's what essentially that does. And then, as you kind of mentioned, the telematics using CAN, whilst not using Greengrass, it obviously we've got that data, so things like RPM. Now, obviously, all this data is great, but it's kind of in its raw form. You know, you have longitude and latitude spitting out, and if, you know, the car is stolen, it's not exactly very useful just to see long latitude coordinates moving. You know, they're changing if the car's moving. And so we need some way to visualize this. So this is where it leads on to Freeboard. Now, this is an open source bit of software that essentially its purpose is to visualize IoT data. And this is running on an EC2 instance that I've got in my account. And as you can see at the top, well, I've got the time, but then the GPS coordinates are now a Google map. So this will update in real time and the pin will move as the car moves. And actually what we did was I had my laptop on my lap with the Raspberry Pi plugged in and the GPS receiver, and we drove around our town and the pin was moving. So it's great, you know, obviously, hopefully it doesn't get stolen, but if the car was stolen, you'd be able to literally track it on a map. And then as you can see below, these are the car telematics. So you've got like RPM, for example, and those little sliders, again, they update in real time. So you put your foot down and the RPM moves, literally the slider moves like this. So it's a great way to sort of visualize your IoT data. So that kind of really like wraps things up that I've been doing. Obviously, I'm going to be working on lots of other things in the future. But I'd like to say that Greengrass is a great way to sort of bring AWS capabilities to sort of physical hardware. So there's lots and lots of, you know, capabilities with this, and you don't have to use it on a car, you can use it on other things, you know, turn on your lamps and stuff at home. So I hope this has kind of like inspired you to use, maybe check out AWS Greengrass after this, and yeah, hope you've enjoyed the talk. Thank you.
Thank you. You almost did it in time. Perfect. Thank you very much. So as we are pressed for time, questions and answers you will do outside on the side of the tent. If you're leaving, please take a look around you and take any